Hello, and thank you for joining me on this guided project. Today we're going to be doing a linear regression. We're going to use a few linear regression models, but this is designed to be kind of a level one, an easier project to get started for my students helping out or going through my machine learning program. Okay, so getting started, we'll import our drive. Very important, so we can connect our stuff just in case we want to save files. Kind of a habit that I always have, I always connect my Colab to my drive. Okay. And usually when I start building these, I actually usually import the data from my drive before putting it onto my GitHub. So here we're going to do is we're going to work with pandas, numpy, matplotlib, pyplot, and cbind. We're also going to work with some pre-processing libraries from sklearn. So we'll do sklearn preprocessing, import standard scalar from sklearn dot linear underscore model import. So we're going to import a few models today. They're all linear regression. It's just kind of really the first step at data science, throwing more and more math at the problem of, or the limitations of linear regression. So we're going to start though with linear regression. So capital L, linear regression, capital R. Then we're going to do lasso. And then we're going to do ridge. And then we're going to do ElasticNet. And this is my favorite one, ARDRegression. Capital ARD, capital R regression, and then we're going to do SGDRegressor. Okay, SGDRegressor. So import those. We're with a few models today, but they're all again linear regression. So it's good to kind of try more than one model at a problem. I would usually throw linear regression, a simple one of these simple, usually ARD regression or SGDRegressor. I would usually import those or try one of those along with ensemble methods. So these are still very valid models, although again, linear regression has its limitations. Because of those limited limitations, it can be a good predictor on new unseen data because it generalizes. That's just what it does as the best it can do. Anyways, so here we're going to import this data set came as, and we're going to do a house price prediction for this simple linear guided project. And this came with a train and test set. So when we have those, I'm going to create one file for the one data frame for the train and one data frame for the test. So data frame underscore TR for train, data frame underscore TS for test. And it's truthfully a little bit easier to change the R and the S. You always have to change variable names. So I just like the short form, and truthfully, I got really tired of writing EST to change train from test. So just a short form saves you a little bit of time. So looking at the heads of train and test, what we're going to do is as we get into the EDA, I'm going to make a palette of different colors. I got them from colormine.io, really good palette maker. And just so I can use different colors than the standard kind of default settings on everything. So here we're going to do dftrain.info to look at the data types, and here we can see we have all integers, not common, but we have all integers today. So there are likely going to be some of these are categories, but we'll inspect it as we go through the data. So starting off here with a loop, so we'll go 4 feet in df.columns. This gives us a list of all the column names that we'll loop through. We're going to start off with a swarm plot, so sns.swarm plot, and we're going to go inside this. We're going to go data equals df train. So we're only going to look at the train data. That's the kind of the idea where we've never seen, we don't want to see the test data, to be as thorough and diligent as we can in making sure our data is going to be predictive on new unseen data. We're going to do the feature as the y variable, so it's going to be on the y-axis. S is 4, so the size of these are smaller, and then color palette, we're taking the first position of the color palette that we created up above. We're in plot.plt.title down below, and then plt.show our plots. And this will take a little while to run. It is uses some very complex mathematics to try and put it so that each dot is not on top of each other. This I don't think is very pretty, but I think it's very interesting to inspect this data and really get this extra level of texture. Really, here you can see this would almost look the same in really even a box plot or just a histogram. But really, you see here, you're starting to get quite a bit more texture with really where these things, this is a small little spot right here. This line is really where these are on top of, not a box or a box-in plot would generalize this quite a bit. So you can get some extra level of inspection from this. I would say it's not the best graph to share with your boss, though. It can lead to some interesting insights, though. So one thing also notice, we're getting this error. So while this is finishing continue, let's stop this from happening again. Let's plot something that looks a little bit better, a little bit more general, to see if we notice anything different here. So again, I'll leave it up to you to inspect those. So warnings, let's import warnings. Then we'll go warnings.simple filter, and then we'll just give it the string ignore. So we're just not going to get those warnings anymore. Okay, so let's do a violin plot and see if we can get some more insights from this. So we'll go 4 feet in dftrain.columns, sns.violin plot, and then we're going to go x. We're going to data equals dftrain, x equals feet, and then we're going to go color equals palette. The palette we created up above, and we're taking from the 5th position, position number 4, we're taking that. We're going to give the title, we're going to give it feet equals right here, feet. Okay, so we'll run this right now. Okay, and then we get our plot of the violin plots right here, so really nice. Okay, let's go down into the bivariate plot. So just looking at the columns, just to peek at those. Notice that we have quite a few today, so I'm just going to do, when I give the data, I'm going to train the iLock. I'm going to take all of the rows and only the first 6 columns. Okay, so just do a little small condense. I tried this first with more, and it just looked, it's too much. So I didn't know that this was going to look ugly the first time, but it did, and so I reduced the number of plots. While this is loading, we'll do the second one here. So we're going to do a second plot, so sns.pairPlot, and we'll do dftrain.iplot, and we'll do kind equals hist. And this gives us the 2-dimensional histogram, which I think can add a lot more texture than just the scatter plot by itself. Okay, so we have our 2 pair plots done. And I'll leave those up to you to inspect those, and it's really amazing the amount of detail you can see from those. So we'll start with, I think a correlation matrix goes hand in hand with this to give us some better understanding. Are we really seeing a correlation here? Like you can see here, very, very tight. There are some very, very tight, especially in the first one right here. Total basement square feet is seems very correlated with the greater living area. So bigger houses have bigger basements. Anyway, so here what we'll do is we'll do fig size. So feature, plt.feature, fig size, and then we're going to give it a tuple of 11 by 7. So 11 is the width, 7 is the height. We're going to then put into a seaborne heat map. Oops. We're going to do heat map, if we can spell that correctly, and then we're going to put into that not just the data frame, but dataframe.corr, so we get a correlation matrix. I find it really just truly very valuable to note and show the actual correlation on these plots. The coloring is great, but it's usually not just enough. And we're also going to do this a continuous color, so we're going to do cmap equals spectral, and this gives really highlights it very nicely when there's positive and negative correlation. So this is a good one to use for that. It's on seaborne, it would also be good to use this diverging palette. Okay, so here you can see we have very external quality and kitchen quality have a very strong negative relationship. Well, everything seems to be relatively positive or positively correlated. We'd be really paying attention to the sales price and what is correlated with the sales price, because that's what we'll be predicting today. Okay. Here we'll do one thing. We'll do DF trains. This is great, but again, we want to focus on the sales price. Let's just look at the correlations with that. So we'll go DF train dot core with, and then we're going to give it the series that we want to have the correlation with. We're going to sort the values. We're then going to plot the values, and we're going to do a bar plot. Color equals palette, fig size equals 8x4. This is a nice feature of Pandas that you can do the fig size right inside the function. So a little handy to do quick, easy plots. And here we're doing plot.xticks and rotation just to get it a little easier to read those. Okay. And you can see here that we see the sales price has a perfect correlation with itself, but overall quality has the next biggest positive correlation, and external quality has the highest negative correlation. And so I write these observations down. So it's good to have references, and inspecting plots doesn't take too much time, but having a nice simple way to come back to your notes is really helpful when you need it for pre-processing later on. Okay, so heading into the pre-processing section, we're going to start with looking at handling the outliers. So we'll do the bins of overall quality, and we can see here we have some outliers, not substantial. We have 2, 3, and we're just going to clip those in. So move those onto the inside. Outliers do really make your model unpredictive. Just as they really affect an average, they would really affect the average best coefficient that is found. And so they can be very, very damaging on, especially for linear regression, on predictions. And so you can see here, just clip those in. We're going to clip lower 4, upper 9. Okay, and again, this is kind of adding bias. And whatever number you decide to clip it in, or how you deal with these outliers, you need to deal with them, or you should deal with them in some way, but how you do adds a lot of bias and really will affect how your model predicts, better or worse. So it's good to experiment with these. Is a good opportunity to experiment. So here we're going to do total basement square feet. So we'll go kind equals hist, and we'll plot the histogram of the total basement square feet. We're going to go clip equals, and we're going to go upper equals 2000 and upper equals. So I just kind of brought it right into the distribution. Maybe left it a little bit higher, just so that there is some texture there is representing that it is a higher value, but brought it in so that it's not all the way out here at 6,000. That's kind of unnecessary. And then plotting the histogram. So this is what it looks like when it's clipped, truncated. So plotting the first floor square feet here, going to do the same thing here, and to mix up what we're practicing with, we're going to go the dataframe underscore train square brackets, the name of the column that we're truncating. Dataframe underscore TS, and then TS stands for test, so train and then test. So we're doing one for each, and we're clipping again, just like we did up for the last two. And plotting the bins right here. So here we can set the bins. Let's do 20 again. Actually, let's do 15. We can change this up. And we can do 15 here. So really just adding more. I think the standard plot is only 10 bins, and I think that hides data a little bit. So it's better to do a little bit of a larger number, but again, within reason. So here we'll do one more here. I did the rest for you just to be a little bit nice. It's good to practice a few times, but we don't need to do it so many times. So doing the ones for upper total rooms above ground, and then doing the garage area. So there's a lot of outliers. It's pretty typical with a real estate data set is that there are some outliers. Financial data in generally has that kind of exponential distribution. Okay, so here we're going to deal with, we're going to bucketize a few of the columns. So let's look at the distribution of years built first. And we can see, we could truncate this in a little bit, but it really just seems really not something that we could just deal with in that way. So we can see it's not a very good distribution for predictions. Either the average would not be really representative of this distribution. So the way to deal with this outlier, this awkward distribution, is we're going to bucketize it. So we're going to cut it into even sections. I think this is really good for time periods, really tend to work this way naturally. So we're going to bucketize. So we're going to do a pd.cut, the train distribution, the series, the column from that. We're going to do none equals bins, or we're going to say bins equals a list of our bins. And for 4 outside bins, we're going to have 3 labels. Okay, so 1, 2, 3, and then we're going to do the test set. So here, bins, and then labels right here. So, okay. And we look at that, we can look at the value counts, dot plot, and we get those 3 value counts, the number of times each one of those appears. This is breaking it into 3 different groups. You can do as many as you want. Again, this is where you can add a lot of bias. You can make your model more predictive. More data supports more. We're going to one-hot encode these. So we'll create a 1 column for each one of these. So we need enough data to support more columns. So it's good to kind of keep that in mind when you're doing this on your own projects. Okay. So we're going to do this again. So we're going to do pd.cut, and that's how we'll bucketize the column. pd.cut, we'll cut it into little sections essentially. We're going to do the bins, and we're going to do a lot more this time. 1, 2, 3, 4, 5, 6, 7 outside edges. And so then we would have 6 labels for the 7 outside edges of the bins. Okay. And we see here we get quite a few. I really think, again, it really depends on your data set, but breaking year into the one-hot encoding that we'll do with these categories is usually a very good way, because time kind of doesn't have necessarily exactly a linear relationship. Okay, so we're going to one-hot encode. So just looking at our features, we have our 2 categories that we just created from the pd.cut. And we also have full bath and garage car, which I had mentioned up above in the observations as to, I feel that they would be good one-hot encoded category. I don't know if there's a linear relationship, 1, 2, 3 exactly adds the same portion amount of, value. Probably not. It's probably, an interesting, maybe an up kind of down, or a slow kind of increase after a certain point. Same thing with garage cars. So I thought those would be good ones for us to one-hot encode. What we're going to do is, for the train and test, like we've done for the whole workflow, we're going to do pd.get_dummies, and we're going to go give it the data set. We're going to do the whole data frame, and then we're going to give it columns right here, and then we're going to go get_dummies, and then we'll do columns again here. Give it the whole data frame, and then give it columns equals our features that we want to one-hot encode. So if we look at the head of that, we can see here our one-hot encode. So full bath, when it's not true, it'll be 0. When it is true, it'll be 1. Full bath, when it's true, it's 1. When it's not true, it's 0, and then so on. And this allows our model to develop a coefficient for each one of these, basically coefficient times 1 when it's true, and then when it's not true, it'll be 0 and not active. Okay. So printing a list, so we're going to get into the modeling section here. So printing a list of our features, so we can have choice and flexibility into what goes into our model. So copy and paste it right here, and equal to features, a list of our features. Took out the ones that I don't want to use because we one-hot encoded these for other ones. So we have these in a different format. I'm going to say target equals our sales price. Down below for train, we have 2 different data sets. So data frame train, we're going to take features from that and assign it to X train. And then we're going to take target from our data frame train and put it to Y train. And then do the same thing for test down below. And we'll look at the shape of those. Oops, got to run the feature list first. And then here we go. And so we got our shape suite. So we have 700 rows in our train, 26 columns. So we increased the number of our columns by quite a large amount. We honestly have not really enough columns, maybe the maximum amount of columns that we should use, the upper limit, when we have this 700 columns. So we could think about maybe reducing this to some extent, or try experiment with more, try experiment with less, then I bet you probably get a better prediction. Okay. So here we're going to do our standardized, really important, especially for linear regression, to make sure all of our features are in the same scale. So we're going to fit it to our train set. The mean and the standard deviation used in our scaling, we're going to get only from our training set. Then we're going to go standard, we're going to assign this to standard scalar object. We're then going to go standard scalar dot transform, and we're going to do our train set, and then we'll transform out testing. And we'll run that without an error this time. Okay, so we're getting to the modeling now, and we now have our X train and X test standardized. So we're going to go linear, or reg equals linear regression. And we might as well fit the model here. I like to just save the line of coding. So fit our model as we're calling it. We're going to go reg score for our train and our test data right here. And we get an 80 on our train score. Okay, so next we'll do the lasso model. So LASSO, capital L. We're going to assign it to lasso. We'll go lasso.transform, or sorry, not transform, score and score. Score and score. We'll get our scores. So we'll assign those to two different train and test scores, and we'll put this into a data frame right at the end to take a peek at it. And so here we're going to do ridge, our ridge model, and we're going to go, we're giving it an alpha, which controls the strength, and there's plenty more. Go look at the documentation for ridge, but alpha is usually one of the main ones you want to play with for hyperparameters. It controls the strength of the regularization. So ridge.score, train, and we'll do y train inside here as well. We'll get the score for that. Do the same for x test and y test. Get the score and look at those. Okay, so we'll now do ElasticNet. So we'll do REGR, ElasticNet. I think it's like linear regression with just lots of regularization. So RegR, ElasticNet, or that's my understanding as to why they call it RegR is the normal one for this. Okay, regression with lots of regularization. Anyway, so fitting it, and then we're sending it to reg, getting the scores of both of those, just like we've seen before. And again, playing around with the hyperparameters will definitely change your scores. So recommend spending some time on that. And here we'll do ARDRegression. Regression. And dot fit it at the same time. So we're fitting it, we're initializing it and fitting it at the same time, getting our coefficients. We're going to assign ARD and ARD right here. So both of those. And then what we're going to do is the last one, SGDRegressor right here. So SGDRegressor. We got a few more options here. This uses stochastic gradient descent to find the linear regression, which is the same thing that is used in linear in deep learning models. Basically, is another way to find a linear regression. And so it should give us the same answer, roughly the same answer. And so we'll fit this as we're calling it here, and we'll get the scores for it, and we'll get, and we'll take a peek, and we got roughly the same scores, which is very interesting. You would expect, and I have normally seen that we have different scores for linear regression. They usually do, but that's very interesting. So, and it could have to do with the pre-processing we did. We allowed for lots of the non-linearity that is what lots of the extra mathematics are trying to do in these other models. So, okay, so we're going to do right here, we're going to assign our train, score reg, and then we'll do, and when I say score, I like to leave out the vowels when I assign variables to make it a little bit easier to write. So here we'll assign SCR_TR_lasso. Okay, assigning that to a list of scores and assigning a list of our test scores to TS scores as well. And I always put, when it's a list, I always put an S on the variable name just to kind of keep track of that. It's a common syntax, and so it's good to kind of stick with that. So in here for their model names, giving a list of our model names, we make sure to put in regression, ARD regression. And then what we're going to do is build a dictionary of our scores. So test score is the key, and the value pair is train scores. And then test score or key, and its value pair is TS SCRS. Okay. And we're then going to put our dictionary into a data frame. And we're going to make our index equal to the list of models from up above. So they will take up just a nice on the left-hand side. And this is what I always do. I usually make some changes, restart, run all, come back down to the very end and take a peek at this kind of printout right here. So it's really handy workflow. And you can see we did very similar on these. I did play around with them to try and get the best score. This was the best that I could do for each one. So try and see if you can find better hyperparameters. Definitely let me know in the comments. Don't forget to like and subscribe, and I will see you next time.